Okay, so I'm going to go over the general problem of background estimation, why it's important, what we're doing right now, what limitations that procedure has, what we're doing to mitigate those limitations, and our project plans for sky estimation in the future. So sky estimation is another one of those problems that that seems simple on the surface, but is much more challenging when you want to get down to precision photometry. So you teach your, hang on, let's figure out how to advance. When you're teaching your students how to do image reduction, it's easy, right? You do your bias subtraction and your flat fielding, and then you have an image where you want to measure the flux of some star. And look, you've got this offset bias because of the night sky emission. And what do? You measure this mean offset, subtract it off, and then you can count up the flux from your star and rest assured that you're only counting flux from that star. So what do you find? Okay, so what happens if you have a ramp? Well, in that case, fine, you measure the flux on one side and the counts on the other side and model it by some ramp, subtract that off, count up your flux. But you know what, it's really not a ramp, it's more like a polynomial, so maybe you should use a polynomial. Oh, but look, is that even background? Is that even night sky emission at all? Do I even do background estimation in this, or is this where I need my deblender? With this, if you look at this blue line, what is the contribution due to the star that I'm measuring? The reason this reduces to a deblending problem is because it is the same problem as deblending. The background is any flux that is not in your model or not in your, that is the contribution to the flux not for the particular source that you are measuring right now. And there are so many different ways to do background estimation wrong. We've seen numerous cases. I mean, one common problem is when you over subtract in the annuli around bright stars. One of my favorite examples was when Eric Huff was trying to measure the magnification signal in SDSS Stripe 82 data. And with the images with the over subtraction problem, he noticed that in his signal, the background galaxies were magnifying the foreground galaxies, which of course is impossible. We also see this in our own photometric residual. So Eli's going to explain this in more detail later today. But after he ran his photometric calibration code on our sources, and then stacked the residuals by CCD coordinates, he got this pattern. And this pattern, I will argue later in this talk, is due to problems in the background estimation. And so before you freak out, these are in the sources, which we don't use for science. And also do look at the color bar. It's plus minus 2 millimag. So we are talking about small effects here. But whenever we see these kinds of patterns in residuals, we get really excited because it means it's something you can account for and fix. When talking about background estimation, I bet everybody in this room is thinking about background slightly differently. And that's because there are 3 main sources of background, and the distinction is really important because it determines which algorithmic component in the pipeline should be responsible for removing it. So I split these into 3 sources: instrumental, astrophysical, and then something that is neither nor. So recall, for the instrumental first, recall from yesterday, Robert introduced that larger pixels are brighter, more sensitive pixels are brighter. And we generally try to account for this in the flat field. And I know what you're thinking. Oh, these are multiplicative effects. There's no way that this will imprint in the background. But as I think we showed yesterday and today, multiplicative effects do imprint in the background. And Gary, those, I forgot what you called them, those lithographic background effects are really scary looking. But an example of this is filter transmission curve. So my definition of instrumental background is the background that has coherent spatial structures in CCD and focal plane coordinates. So you take many visits and this imprint of your ISR, of your instrument signature removal is in the same place. It has the same structure in every visit. I think Gary did a great job of introducing how this can have really small spatial structure. So Robert showed yesterday how we also have these residual CCD and AMP offsets, which follow the same general pattern in every subsequent visits. And this also, and even though fringing is a multiplicative effect, it does imprint in the backgrounds as well. So instrumental background, anything that is fixed in CCD and focal plane coordinates. Astrophysical background, on the other hand, is anything that's fixed in sky coordinates. So you take multiple exposures of the same part of the sky, and you see, for example, galactic cirrus in the same place. You also have the diffuse scattering halos from the atmosphere seen especially around bright stars. And while these change in amplitude, they are spatially fixed because the stars are fixed. So we're interested in measuring the stars and galaxies behind this bright star, but we're also interested in measuring the stars and galaxies behind the wings of bright galaxies, or behind intercluster light, or in front of the unresolved stars and galaxies. And then in the limit of the deblending problem, neighboring stars and galaxies can also be considered background. Okay, so instrumental is fixed in focal plane, astrophysical is fixed in sky coordinates, and then that which is neither. So I call this the temporal background, but this is from terrestrial origins or solar system origins. And this is your typical moonlight background, anything that changes from visit to visit. This is loud. This is also from air glow, from your atmospheric emission. It can also be from zodiacal light. And I know what you're thinking. This is kind of on the border between astrophysical background and temporal background because, sure, it's fixed over the course of one night, but it does vary over the course of a year. And then, an especially fun source of background are ghosts, the scattered light from bright stars. So Robert and Jim Gunn took this series of exposures of Arcturus at increasing, with it increasing distance from the center of the focal plane. And you can see how the ghosts change, or it depends on the source's position in the focal plane. It doesn't even have to be in the focal plane for the ghosts to be visible. We also distinguish between ghosts and ghoulies. The ghosts are the scattered light from the main primary surfaces of the optics, and the ghoulies are the scattered light off of the secondary components, like the edges. And the difference is that the ghosts can, in theory, be predicted and subtracted off, but the Ghoulies cannot. So this is a prediction by Josh Myers using his Batoid ray tracing code. And it reproduces the actual ghosting of Arcturus pretty well. Now, I don't, you can predict the positions of ghosts in theory and subtract them off. I have seen this work. You can predict and mask the ghosts in practice. I have never seen predicting the ghosts and then subtracting them in order to recover sources underneath in practice. If you know otherwise, please let me know. But I suspect this would be extremely difficult because there are caustics, and if you get the position even slightly wrong, I imagine this would leave very, very bright residuals. So the distinction between these sources of background are mainly for who's responsible for removing it. And I see background subtraction as the step in between flat fielding and deblending. Whatever imprint is left over from ISR, the background subtraction must account for. And whatever background is not subtracted in the background subtraction stage, the deblender must account for. So with this in mind, what do the pipelines do now? Okay, recall from yesterday, this is our procedure of single visit processing. And I'm going to present the procedure for background estimation as of the HSC public data release 2. This is slightly different than what we do now, but only slightly. So the first step is to remove this instrumental background. The next step is to remove an initial naive background model. And the way we do this is you take the post-ISR CCD. This is done per CCD. We run detection, mask out all the detected pixels, bin it up into 128 pixel bins, take a robust mean of each pixel, and then model it as a 6th order Chebyshev polynomial. Subtract that off, hold that to the side, and the result is a processed visit image. The sources are measured on that image. But those are not the images that we co-add. Before co-addition, we also do a full focal plane background subtraction. The way this works is you first pre-compute sky frames. And these are kind of like Gary's robust PCA components, except they're only one component. It's only the first component. It's a median of all the normalized focal plane skies for that particular filter. So we pre-create those, hold them back, and then for a single focal plane, we bin it up into 8,000 by 8,000 pixel superpixels. And so remember that our CCDs are 2K by 4K. So these pixels are bigger than a single CCD. And this will pick up the large scale features that vary from exposure to exposure, like the big gradients due to air glow and moonlight. And then after we remove that component, we subtract these sky frames from the exposure, normalized across the whole focal plane. And this picks up the small scale features that are constant between exposure to exposure. So for that same CCD, this would be what the SkyCorrection PDR2 background would look like. You can see the smaller scale structure in this that you couldn't see before in the local per CCD background. And then using this background subtracted from each CCD, we co-add the images. And then in PDR2, we did not do any more background subtraction after that. That was it. We measured and we did detection and measurement on those images. Okay, so how well is this working? What are the limitations and what are we doing to fix it? Going in order from instrumental to per CCD to full focal plane. How's this going? Okay, so the ISR component is not doing great. And we have these amp to amp offsets left in and CCD to CCD offsets left in. And I mentioned at the beginning that this is causing an imprint in the residuals of our photometric calibration. So Eli's residuals show this pattern. You see these ramps, and these follow naturally from offsets in a background if you're doing per CCD background subtraction. So just as an example, if you have an original post-ISR CCD exposure with offsets in the amps, and you try to model this background with a 6th order Chebyshev polynomial and subtract this background model, should not point at my screen. If you try to subtract this background model from this image, you're going to get this background subtracted image with ramps, which is exactly what we see in these these residuals. So this is something that we want to fix for photometric calibration. And this was in case you did not believe that we actually see these offsets in amps averaged over the focal plane, but I think that's clear. So what are we doing? What are we doing to fix this? Okay, so we're approaching this from 3 angles with an increasing, or rather with decreasing principle. So Eli's working on improving ISR, and we're doing this through taking flat ramps, so a series of flats with varying exposure times to find this hidden variable that we're not accounting for. We're also prototyping a robust PCA, and this was inspired by Gary's work that he presented earlier. So we've been applying the robust PCA algorithm from Emmanuel Candes with some, this is also a work in progress, and inspired by pan-stars, at the very least, we can do some kind of empirical amp-to-amp continuity or offset correction. And Lee Kelvin and Chris Waters is working on this. Okay, so what about the full focal plane background subtraction? So the PDR1 is what we were doing, was the data release before PDR2. This is what we were doing initially. And this is a coad. And this is a coad of the images that had only the local sky subtraction removed. So we did the per CCD 6th order Chebyshev polynomial, subtracted that, and then co-added those background subtracted images. And this is, so the over subtraction around this is obvious. And this was particularly bad because the backgrounds that were subtracted from these individual images are back at the calyx level, at the time series level. And so if somebody wanted to add this background back in to their coad, it would be extremely difficult because you'd have to, it's possible, but extremely difficult. So looking at an over subtraction around bright objects standpoint, the PDR2 background looks a lot better, and the low surface brightness community was really happy with this. However, everybody else was really unhappy. And the reason for this is that this very large scale background subtraction left a lot of light in, and this pushed more of the responsibility down to the deblender. The deblender does not produce reliable photometry with enormous monster blends, and many more sources were either in a large blend like this, or were in the scattered light from bright stars. So the effects of this were that we had to increase the masks of the bright stars, reducing our survey area by 30%. And if you wanted to do weak lensing with this data set, for example, it would be much harder to get a clean sample. Your clean sample would be a lot smaller as a result. So as a result of this, we decided to do a very terrible, very aggressive 128 pixel bin spline background subtraction to the coads before doing detection and measurement. And the argument here is that because it's a coad level background subtraction, it's trivial to add it back in if you want to recover this. So the red mask areas, those show your detection footprints. Oops. And this is the PDR2 version, and this is what we're doing on the master branch of the stack right now. So you can see that right now we are now over subtracting around bright objects yet again. Okay, so let's put a pin in the deblending astrophysical background problem and talk about just the wings of bright stars. This figure is from Morgan Schmitz. He is working on subtracting light from bright stars. The orange rings are the boundaries of the masks in our PDR1 backgrounds. In PDR2, we lost all the sources that are now in the extended bright stars footprints, which is these orange points here. To mitigate this, in collaboration with Raoul Infante-Sens, we are working to model and recover the wings of bright stars. Sorry, working to model the wings of bright stars and then subtract them off in order to recover the objects that are behind them. So this is a schematic of Raoul's work with SDSS Stripe 82 data. He coads all the bright stars at a variety of magnitudes to probe different parts of the star's profile, and then normalizes this to each of the observed stars, and then you can see that they subtract off quite nicely. So this procedure is becoming more and more ubiquitous in the low surface brightness community. Okay, so in general, those are two known problems with the existing background subtraction procedure and plans for fixing them. I'm now going to go through the project plans for background estimation as a whole. So this is how we see background estimation happening in production. Okay, so the first step is still remove the discontinuities and other high frequency structure due to instrumental background when you're still in CCD and focal plane coordinates. If you try to do this after you have already warped to the coad plane, to the sky map projection, this gets a lot harder. We will probably still continue to use a local per CCD background for measuring sources. And then for the temporal background, remember this is the gradients in moonlight, airglow, ghosting. We can utilize the fact that they change in time. So our plan is to account for these during the co-addition step through a procedure of matching the backgrounds before co-adding. The goal of this would be to leave in a common mode astrophysical background, but remove the time-dependent backgrounds. One realization of the sky would survive, but we can subtract this at higher signal to noise. So we do not do this currently in HSC, but we implemented this for the 2013 data challenge, where we co-added Stripe 82 data. And in this procedure, we started with a reference image. The point of the reference image is to lock neighboring patches together so that the track remains one image and has a coherent background. Then for every input image, you find the difference between that input image and the reference, model the difference, masking out detections in bad pixels, and then add that model back to the input images, matching it to that of the reference image before doing your co-addition. When we had done this in 2013, this was generally successful. So in the background matched coad on the right compared to the background subtracted coad on the left, you can see that it does maintain the astrophysical background as one realization of the sky. Now, this does not solve the problem of sky background estimation from the astrophysical component. And this is really the hardest problem, in my opinion. And this is because, Gary said it best, the distinction between signal and background is in the eyes of the beholder. Or as Robert says, the background is the mean level of any flux which isn't correctly accounted for by your model. You might be interested in measuring this source and this galaxy's background, or you might be interested in this background. It all depends on what you're interested in. I word this as one woman's garbage is another's treasure. So we found that asking the deblender to deblend the images and take care of this by itself did not work well. So this really put a lot of stress on the deblender. There were cases where almost the entire patch was a blend and the deblender was working on the whole patch. This not only produces unreliable photometry, but there were some cases where this would suck up a terabyte of memory as it was working on the PDR2 data release production. So we need to push some of the responsibility down to back in time to the background subtraction stage. we do want to do this. We do want to do this in co-edition because it needs to be simple for people to add the backgrounds back in to be able to detect low surface brightness features. And remember that we are committed to making the images as useful as possible for as many science cases as possible. So we will be doing some astrophysical background subtraction, though not necessarily with this super aggressive 128 pixel background. You will always be able to add this background back in. And help us help you by making this background model as useful as possible. So our general, right now we are subtracting off a background of one scale, but what we could do instead is produce a hierarchical model of the background at many scales, because people are interested in many scales. And then in this, if we had a hierarchical background, people could add in the backgrounds of the scales that interests them. So this is one possible option for this is wavelet decomposition, which is really popular in the cluster analysis and X-ray community. This was from a talk I saw by Rachel Livermore at a Epica for ionization meeting. But I think, but we need some input from the community on how to make this most useful for everyone. So the plan summary is we commit to getting ISR right and building the ability to handle the amp-to-amp and CCD discontinuities. We will handle the temporal background, everything that's not fixed in focal plane or sky coordinates, by producing background matched coads, subtracting the wings of bright stars. And on the astrophysical background level, we cannot have the deblender be responsible for everything. So we will be detecting, deblending, and measuring on a background subtracted image. This background model is available to add back in, but it'll be hierarchical or multi-component so that users can apply a spatial scale that we're choosing. So I would love to hear from you about your experiences with the edges of ghosts, what you think about the multi-scale astrophysical background, and more about what you've learned about the instrumental background. Thank you.
Thank you, Yusra. That very comprehensive overview of the project's plans for background estimation. We have some questions. Just let's see. We'll start with Richard.
Oh, hi, it's an issue I asked yesterday and was asked to be deferred. In DES, I think at Y4, we switched to a full focal plane solution for sky. And almost immediately we noticed significant problems with difference imaging that was, on moony nights. And I don't remember the details of how close and how bright, but it's just something to be aware of. And people working on the difference imaging, if you get a chance to test HSC data in bright moon with these algorithms, please do so.
Okay, thanks, Rick. So the answer to your question was that these full focal plane backgrounds are extremely problematic on any nights, mainly because they assume that there are no amp-to-amp offsets or CCD to CCD offsets. However, that assumption is not true. And that effect is especially great on nights, on images with shorter exposure times, or like you're saying, nights with higher than usual backgrounds. So pulling up an example of a focal plane. This has had the full focal plane SkyCorrection background subtracted from it. And while this was not taken, I looked up the moon phase of this night, and it's a waxing crescent, 31% illumination, but it was, so this isn't moonlight, but it was taken at around 5:30 in the morning. So I think we might be looking at twilight here. But yes, you get, these are definitely worrisome. We see the same thing.
Okay, thank you. Rachel, you have a question?
Yes. Okay. First of all, thanks for the talk. It was really interesting to hear about the plans. This question is kind of in the spirit of like, how can the science community be helpful? And in particular, what I'm thinking of is the fact that, you know, in my experience in SDSS and HSC, some of the progress on identifying issues with sky subtraction and how it affected different science cases were driven sort of by, you know, one working group goes off and does some analysis and finds something, and then, you know, sort of complains, and then something gets changed, and then another working group finds it broke things for them. And so I was imagining it is probably helpful for you if you have in advance a set of like, here are the ways to identify like this specific, you know, quantitative measurements to make to understand how the sky background is affecting weak lensing and large scale structure versus people who care about nearby galaxies and so on. So do you have a set of those metrics and code to carry them out as you're developing these algorithms? Is that something you don't have but you plan to have? Do you want input on it? Is there some way we can help, or are you all good?
Okay, thank you. So that was your experience is a pretty good description of what happened to us through the HSC, the background subtraction procedures in the HSC data releases, as you saw with the difference between year 1, year 2, and what we're doing now. Yes, please send us your metrics. Right now, our metrics that we track with, sorry, we'll delete. The metrics that we track include sky objects. So we insert, we plop down some centroids on areas of our coads that have no detected pixels in them, and then pretend that there's a source there, and then do the whole suite of measurements on them, like PSF estimation, or sorry, like PSF flux. And so we do track the photometry of these sky objects, but that is definitely not enough. And it does affect all science, albeit indirectly.
Right. It sounds like this is maybe something we should take offline for later, but I'm sure that such a list of metrics could be made and code might exist for some of them. Okay, thank you.
Okay, we'll take one more question from Tony Tyson.
Hi, wonderful talk, thank you. I guess I have one fundamental question, and that is that for stars, if you're trying to get the flux, then it's sufficient to look at the sky level around the star and do something, for example, like you mentioned, PSF photometry. But in the case of very low surface brightness galaxies, you know, there's a difficulty there. And so the actual zero level of the sky matters in that case, as opposed to the apparent sky, as you said. So it seems that it would be useful to have a global estimate of the actual sky zero over, over the entire focal plane, from which one could then build up a model of what else is there, such as dust and everything else, rather than leave it to the community to go back and re-reduce the data.
Oh yeah, I am not proposing that we leave it up to the community to re-reduce the data. Let me see. Okay, so ideally, you would be able to use you will be able to do detection in the backgrounds, the astrophysical background models themselves. Okay, so at the instrumental stage, we can remove all the instrumental effects. During the coaddition stage, when we have the whole time series available, we can remove the temporal effects. Now we're just talking about what happens when you have the astrophysical background left. That's one astrophysical background remaining. We can model that at multiple scales. And I like your suggestion that that garbage is someone's treasure. It's not just their treasure to add back in and redo their analysis. That model, those models themselves can be useful as data products. And that would be our goal.
Yeah, I completely agree. It's just that in order to really make a model, you have to understand where the zero really is of the sky. And as you mentioned, things like S-extractor over subtract the sky simply because it ignores other components that are below detection. So is there a bias? I guess my question is, would there be a bias in this astrophysical sky background done?
It would be at tracked scale. So while you could have some concept of a zero within a tract, it would, in a tract we're imagining to be approximately 10 square degrees, you would not get a good comparison from tract to tract outside at spatial scales bigger than 10 square degrees.
Yeah, that's probably enough, actually. Okay, thanks. We can discuss it offline. I think this is really important because if we're really going to go down to something like 30-second magnitude or so, we have to get the zero right.
Okay. I'd like to hear from you more about that.
Okay, thank you again, Yusra, for that talk.